All right, we are still working in section 5.5, some theorems about roots of polynomial equations. Now, we already learned about the rational root theorem, but we have two more theorems to learn in this section. The first one is called the conjugate root theorem. And out of our two theorems that you'll see today, the conjugate root theorem is probably the easier of the two. All right, so here's what the conjugate root theorem says. It says that complex and irrational roots occur in conjugate pairs. Okay, so a complex number, and I'll add a couple notes on the side here. Complex would be imaginary, and an irrational root would have a square root of a number in here, like square root of 3, a square root of a number that you can't simplify nicely, okay? So again, complex, we have imaginary roots. Irrational, we'd have the square root of something we can't simplify, okay? Now, what this really means we'll talk about our complex roots first, okay? If a plus bi is a root, okay, so if you have a form, or if you have a root that's in the form 3 plus 2i, a number plus a coefficient times I, if a plus bi is a root, so is a minus bi. And then as far as our irrational roots go, same idea. If a plus the square root of b is a root, so is a minus the square root of b, okay? And again, conjugate means we have the same thing but the opposite sign in the middle. So these two roots are the same except one's plus the square root of b and one's minus the square root of b. All right, so we'll do a couple examples with this conjugate root theorem here. And I'll do two examples here in that same video, both A examples. Okay, so example 1A. We have a quartic polynomial has roots square root of 2 and 1 plus I. What are the other roots? Okay, so quartic polynomial, because we know it's quartic, that's fourth degree, we know we have to have 4 solutions, 4 roots, x-intercept, zeros, whatever you want to call them, and we're only told 2 of them here. But look at this, the square root of 2, that's an irrational number, so that means negative square root of 2 has to be another root, and 1 plus I, that's a complex root, so that means its conjugate, 1 minus I, must also be a root. And keep in mind that we only change the sign in the middle. That 1 stays a 1. So the other roots, negative square root of 2 and 1 minus I. We'll do example 2a here. And then the B video will have example 1b and 2b at the same time. So example 2a. What third degree polynomial function has roots at negative 4 and 2i? All right, so I guess the first thing we have to think about, we have a third degree polynomial function. which means we should have 3 roots. Okay, should have 3 zeros, 3 x-intercepts. This -4 is not a complex root or an irrational root. So we don't have anything special about this. Okay, but if we have a root at -4, that means we must have a factor x plus 4. If we have this root at 2i, though, 2i is a complex root. It's complex because it's imaginary, okay? So if I have a root at 2i, that means we also have a root at -2i. All right, so we'll put our pieces together. I'm actually going to change this x plus 4 to be down one more line. Because if I have a root at 2i, that means x minus 2i has to be a factor, and that's kind of weird to see as a factor, but that's all right. But if -2i is a root, that means x plus 2i is a factor. Right, so y equals x plus 4, x minus 2i, x plus 2i. Now, it doesn't say it here to write in standard form, but if you were asked, let's get that practice. Let's multiply this out, and I would multiply the 2 imaginary pieces first. Things will simplify nicely. So start off, if you have something like this that you need to multiply to standard form, multiply the imaginary pieces first. Life is a little bit easier. So I FOIL these. X times x is x squared. Plus 2ix. That looks kind of weird, but that's okay because I have minus 2ix now. -2i times positive 2i is minus 4i squared. But if we simplify some things here, my 2ix, -2ix cancels out. I have x squared minus 4i squared, but don't forget that I squared is -1. So this becomes x squared plus 4. Which, like I said, how all of our i's cancel out makes it a lot easier to multiply here. X plus 4 times x squared plus 4. FOIL again, x times x squared is x cubed. Plus 4x plus 4x squared plus 16. Okay, and I guess my last step, I want to rewrite this so we are in standard form, highest power to lowest power. And the very last thing, this is representing a polynomial function, so I want to use y equals f of x equals something to represent that this is actually a function and not just an expression.